Okay, there's no tip of the week today, so we'll just move on to Python. I didn't get any suggestions, so yeah. Okay, but instead we'll learn about Cython. Okay, Cython. So Cython is a superset of Python. So it is essentially a language extension to Python that provides you with additional functionality. And so it specifically allows you to specify the types that you're working with in your Python program. And it also allows you to call existing C functions. And so then once you've done this, once you've written a Cython program, you can compile that code, and it generates the C code, the C wrapper code, which is then compiled into a Python extension module. And once you've compiled it, you can use the result just as if it was a normal Python module. So the major advantage of that process is that you can take an existing code, Python implementation, and you can incrementally add more and more type information to it and gain and have performance gains from that. Okay, so it's really kind of a step-by-step process, and the more information you add the more Cython type information you add, the faster your code should be. So there's no need to start from scratch again. And so now we're in the Cython language, and so the first thing that you can do in Cython is you can declare C variables. You can specify which type certain variables have. So for example, if you're working with variables I, j, and k, in normal Python, you wouldn't specify which type it is. In Cython, you can now write cdef int I, j, k. And this tells Cython that these three variables are of type integer. In the same way, you can create floating point values. So f here is a floating point. You can specify that a certain array index is a floating point value. You can create arrays of floats. Here, 42 floats in an array. And you can even create pointers, a pointer that points to a floating point value. So this is something that's familiar if you worked with C before. Then we can also specify, we can also equip functions with type information. So essentially in Cython we have three types of functions. We have normal functions that we Python functions, and their syntax is exactly like the normal Python functions. So we just use the normal def, and then the function name, and then we provide the arguments. So the difference here is that in the arguments we don't have to, but we can specify the types, the type information for the arguments that are being passed in. So it's perfectly valid in Cython to specify that the first argument needs to be an integer and the second one is a string or a pointer to a character. The second type of function that we have in Cython is C functions. So these will be, C functions are visible inside the Cython code, but they will not be visible in the code, in the compiled code when you load it in as a module. So you can use these C functions for functions that are called within your module, but they won't be available later on anymore once you've compiled it and once you import that module. So the C functions you can use for kind of internal functions that are important for the module, but not important for the user. The way you specify this is use the cdef keyword here. That tells Cython to create a C version of that function. And with C functions, you also need to provide type information about the return value of that function. That's what you use here as the type information just before the function name. In this case, our function returns an integer here. And then finally, there are hybrid functions. The keyword here is cpdef for C for C, and P for Python. So when you use cpdef, then Cython will generate both a C version of the function and a Python version of the function. So these hybrid functions will be available as optimized C code and also as a Python implementation that you can call, that you can import from the module and call it out from there. And so again, here we can specify the function arguments, the type of the function arguments, and the type of the return values. So in general, you don't need to provide types. And if you don't provide types in a Python program, then it just defaults to a normal Python object. Right? So it will be slow, it will be generic, but it will be generic, and it will work with any types. So for example, if you have a simple loop, you can just write for I in range n. This is a perfectly valid Python code, but it will only end up in a standard Python loop with all its speed disadvantages. But now, if you specify I to be an integer, so you write cdef int I before you start that loop, then you provided Python with the necessary type information such that it knows that you're looping over integer range, and it can generate C-optimized code for it. So let's look at an example, which is actually quite similar to your assignment. So let's say we want to have we want to integrate over a general function f of x, and so we can't approximate or integrate functions exactly. So we need to approximate that integral somehow. So the way you do that is typically through such a step functions, and you know how much area such a step has, so you just add up. You approximate the function with steps, and then you just add up the area of all the steps. So obviously the accuracy of that approximated integral depends on how many intervals you have. So ideally, you would like to have as small intervals as possible. So in 1D, you might get away with really fairly small intervals even without much optimization. But if you move to 2D or 3D, then this becomes a really big problem. So here's a simple implementation of that. So this is a non-optimized code. And essentially, it implements exactly what I've just talked about. So we have an integrate function with the end and starting and end value, and then the number of intervals that I want to evaluate it on. And this is just how to integrate, how to approximate this integral using step functions. And then we also specify the function f that we want to have approximated. So this is a normal standard Python implementation. So if you do this on a million points, it takes roughly 3.5 seconds. So now, any Python code is also valid Python code. So what we could do is we could just try and compile it using Python. What you need to do is you store this file here, this script here, you store it as a pyx file. So pyx files are Python files that need to be compiled. And you just copy and paste your standard Python code in there. And then we compile it. And we compile it using the Python compiler. So we write Python integral.pyx. This Python compiler will actually generate C code. It will generate the C code and will generate the wrapper code that is required to load in that C code as a Python module. Then we need to compile that C code. So I use the GCC compiler here to actually compile the C code. And you see that there's this integral.c file here that was generated from the previous line. This is the generated code. So I compile that C code, and then I link it into a library that I can later on then load as a Python module. So there are kind of 3 steps here that need to be performed in order to get from your Python code into a module that can be loaded in Python. There's a more convenient way of doing that. you can use setup.py scripts and distutils to automate that compilation process. This is also something that you will do as part of your assignment. So the trick here is that you create a new file in your directory called setup.py. And you essentially, they always look the same. They have this format here. And in the setup function, you call a setup function here. So you import the setup function from distutils.core. And then you call it. That's the only thing that this Python function normally does. You provide it a name of the module that you want to have compiled. And then you specify the modules that you want to have compiled. So in this case, because I only have one pyx file, I just say, okay, please compile all Cython files in my current directory. So you essentially create this file here, and then the compilation step just becomes calling python setup.py buildExt in place. And the in place just means that the output should be stored in your current directory. So there's a little bit of overhead that you need to do here. You need to create the setup.py file, but then later on, the compilation step will be much easier. You can always just run the setup.py file. This is also something that you will find in many existing Python libraries. So when you write your own Python library, or if you download a library from the internet, it's very common that they provide a setup.py file that you can use to install the module or compile the module. Okay, so now we've compiled it. We could use that, but because we just used our standard Python implementation, we only get very minor speedups. So maybe some loops will run in C, but we still need to do all the type checking and so on using the Python API. So there will be a lot of calls going back to Python to check, okay, are we working with an integer? Are we working a float? And so on. So there needs to be a lot of interaction with this Python API. And so obviously the most performant result we get if we go into the C layer and then never leave the C layer again until we have the result. Right? So that's what we want to achieve. So in order to get that, we need to introduce types. So now this is a implementation of the same function, the same integrate function, now with some types added. So first of all, you can see here the integrate f function. Now I added types to all the arguments. So I said that the input, the left boundary of the integrate interval is a double. The right boundary is also double. And then the number of intervals, n, is an integer. I also specified that the output value of my integrate function is a double. And I would like to have this function as both in a C and a Python implementation. And then in here, essentially, I just went through the code, and whenever I use a variable, I also specify which type that variable has. Right? So S here is a double, dx is also double, and then int is the index over which we loop over, and that's an integer. And then the actual for loop down here, this is unchanged. Right? So the actual code we can leave just as it is. It's only the type definition that we need to add. So there's also that one thing, if you want to use math functions in the C layer, then you need to make it available to the C layer. And for that, you use the keyword CImport. Right? So CImport just works like the normal Python import, but it's for the C layer. So I use here the libc.math that provides the standard math.h, the functions that are available through math.h, and I just import this sinus function from that. So then this is still not fully optimal. You can see I still have this f function here that is defined as a standard Python function, so I haven't added types here. But I can also do that. So I just went through the same procedure here, and I specified that the output of f is a double and so on, and the input is a double. This is actually the only two changes that I made. And since f is not used by the user, right, so f is just used as an internal function that is called by integrate f, I don't need to make it available to the Python layer. So I can just use cdef instead of cpdef. Now if you compile this function that is now fully equipped with types, it's going to be roughly 10 times faster than the original implementation. So that's quite a significant speed up. So here's an example of the different speed ups that we obtained. So if you have a pure Python, then the time was roughly again normalized, it's roughly 1.0. Then if we use that Python program and just compile it using Cython without adding further types, we get roughly 25% speed up. So even without doing anything, there's a little bit of speed up to be gained. And then you can add information about the types. So when you add all the types that are doubles, you get another 10% here. And then if you also use the integers, so this, as soon as you use the integers, it will optimize the C loops. You get another 25%. And then if you do a fully typed version, you can shave off another 28% here. Okay, so you can see it's a iterative process to speed up your Python program. So I've only showed you how to do standard types, but Cython also works with NumPy, and there's just some things that you need to keep in mind. So let's say you want to have you have a function that applies the sinus function to a NumPy array. So essentially what it does is it takes in a NumPy array, it creates a copy, it creates an equivalent array of the same length as an output array, and then I loop over all the indices and apply the sinus function on each element, and then return the result. Okay, let's say we want to now Cythonize this function here. The first thing that we need to do, so this is how you use it. So we could create a new function, and we just call it, and then we get the output. Okay, so the first thing that we need to know when we want to Cythonize NumPy arrays is that there are specific D types. So these data, remember, NumPy also always works on specific data types. And there's NumPy data types that we've introduced last week. So you have integers, single, double, complex, and so on. And there's also associated Cython data types that you need to use when you're working with the Cythonized NumPy arrays. And these are basically exactly the same, they're just with an _t. And so I'll show you why this is important now. Because when we create a new NumPy array in Cython, we use again the cdef to define a new variable. And then we just use the standard ND array. But now you pass in the type information in square brackets. And so in the type information, you need to use now the type that you're going to use. So in this case, it's the _t. So this is now the Cythonized Python version. And you provide also information about the dimension. So now, and you specify the variable name. And so then, now you can actually, you define that variable, and now you can actually use that variable to, you provided the type information, and now you can actually create that variable using standard Python functionality. Now keep in mind that here we told Cython that we're going to use a _t. So it's important that our D type here is actually a double. Otherwise, we'll have inconsistent types between Python and C. So it's a bit more complex on how you define these type definitions for NumPy arrays, but it's essentially very similar to also standard Python object types. Okay. So then, here's a Pythonized version of our functions, of the code that I've shown you before. So essentially, it works very similar as before. So, but now when I import NumPy, this is now the Python import. I also C import NumPy because I also want to make sure that NumPy is available to the C layer. And then I generate my NumPy array, my NumPy function here, apply S, provide all the type information. And so now recall here that our output of apply S was a NumPy array. So here, this, what I highlighted here, this is the NumPy array that is returned by that function. Right? So it's going to be a NumPy array of type double T and a one-dimensional array, so a vector. And the same thing is for the input part. Right? So the input is also a one-dimensional vector. And so the rest is very similar. So you just declare the types of all the variables in there. Okay, so then you can go ahead, store it as a PYX file, compile it, and then you can use it just as if it was, the user doesn't actually see anything of the fact that this is now working with C types. So from a user perspective, you just import the apply function from your compiled module, you create a new standard NumPy array, and then you pass it into your function just as if it was the standard Python implementation. Now, obviously, it is important that you pass in a double array here. If you pass something else, then you would have incompatible types. So now, if we do this, you see the timings again. So the pure Python was 1, and then the Pythonized version was 0.205, and the NumPy version was 0.202. So in this case, we didn't actually gain so much using NumPy. Okay, Python summary. So Python is really useful because you can start with once you've identified the slow part of the code, you can move it into an external file, and you can slowly add type information to it and increase the performance on your code bit by bit. It's fairly well supported. It's fairly stable library with a lot of functions that you can use. And yeah, you might consider as one of your first choices if you've identified kind of a fixed code that you want to improve. It's certainly a good option to think about using Python to improve it. There are other packages like Instant and Swig. I taught these last year, but I don't think they're up to date anymore, so you can just ignore that. Okay, so much about Python. Any questions? No. Okay, last part, Numba. So Numba is, Numba is really almost magical library, because what it does is it automates the type information that you had to pass in manually in Python, right? So what it does is, instead of you having to, you just provide when you apply Numba to a function, instead of having to manually specify what are the types of each variable that you use in that function, it will determine it on runtime. So you just run your program as if it was a normal Python program. And when you hit that function, Numba will detect, as soon as you hit that function, right, then you work with specific types. You passed in integers, and you passed in floats and NumPy arrays or whatever. And at that point, you've specified that the types are specified that you work with, and Numba will extract that type information and essentially generate the same thing that you would do in Python, but would have done manually. It will do it automatically for you. It will automatically generate the C code and the wrapper code, compile it, and replace your original Python implementation with the type-optimized C implementation, right? So there's a lot of machinery going on, and but from a user's perspective, all you need to do is you have a Python code, you mark certain functions to be just-in-time NumPy compiled. And then when you run that code and NumPy hits it for the first time, there will be a little bit of delay because NumPy needs to inspect all the code and needs to generate the code and compile it. But if you hit that code 1,000,000 times, the first time will be slow, but the next 999 and so on will be super fast because you're just calling out to the C implementation. That's the idea. And so it's a fairly new project. I think it only started a few years ago. And I think since then it has really stabilized, and now there's crazy stuff. So it even generates GPU code, and you can parallelize things automatically over on the CPU and so on. So it's very impressive what these guys are doing. It is not a standard package, so you need to install it. So if you have Anaconda, then you just type in conda install NumPy. And this is how you use it. So let's say you have so this is a standard example. Let's say you have a function that sums all the elements in a two-dimensional array. So essentially, you take in an array, then you loop over the two dimensions here, I and j, and you add that element into a output variable, and then you just return it. So this just computes the sum over the two-dimensional array. And so the only difference, so this is just standard Python code. The only thing that you need to do in order to use NumPy now is to import the chit function from NumPy, and then decorate the function that you want to speed up with the add GIT function decorator. So now you've marked that function, and that's all. So then you can run it, and you can actually, so this just performs the sum for a specific example, and you get the answer, just as if it was a normal Python function. So you can do a performance test, how that performs to a standard, let's hide this for now, how it performs to a standard Python implementation. So this is the same implementation, but now not marked as a NumPy, not marked with the automatic just-in-time compilation. And so we can use the timeit module now to check how long the Python implementation takes. So that's roughly 535 milliseconds plus minus 15 milliseconds per call. And now we can do the same test now for the NumPy version. So it automatically performs the test. It adapts how often it performs the test to get accurate timings. And so just by one line, adding one line or 2 lines of code, we went from 535 milliseconds to 1.94 milliseconds. Right? So there's obviously a lot of magic in behind, and NumPy tries to be clever. At least from my perspective, the general argument of NumPy is that it tries to be clever by default. So for example, it tries to infer the data types of the arguments that you're using in a function by runtime. You can also have, if your function calls other functions, let's say you're in this integrate case, right? You have the integrate function, but that calls out to another function. In that case, if you really want the other function to be implemented in C also, you don't want to have one function in C and then that function calling out to Python functions again, because that's going to be very heavy. So ideally, you want to stay in the C layer all the time. So that also works in NumPy. You just annotate all the functions that you want to have compiled with the add GIT, and then NumPy will stay on the C layer. It will even try to use inlining if that's beneficial. Yeah.
Will NumPy work with manual timing?
With the manual timing? Yeah.
Or will you also time the compilation?
Yeah, so you will also time the compilation. Yeah. I haven't tested it myself, but that would be really interesting to see how.
But I didn't get the speed either, I guess.
Yeah. So if you get slow result, what you should check is you can actually use caching. So you can make sure that the compiled versions of your code are cached somewhere, so that if you run the program again, that it doesn't compile it again, but it just reuses a previously compiled version. So there's something you might want to look up in the documentation, caching. Yeah?
I was wondering if you could use number to call, for instance, functions in the new libc library.
Yeah. So the question is, can you use number to call out to C, existing C libraries? So yeah, you can do that. I haven't written it down there, but if you look at the documentation, it's described how you can call out to standard, to already compiled C libraries. So yeah, it's possible. It's also possible using Cython. So you can use either Cython or number to do that.
Yeah, you showed us how to do it in.
Yeah, but yeah, I haven't shown it here. I've never tried it, but I've seen it in the documentation how to do that. Yeah. Yeah.
Can you use number?
Yes. Yeah, you can. And check the documentation for that. I think it just works, but you might be able to pass in. You might be able. So in general, number tries to infer as much of the data types as possible, including, I suspect, kind of the shape of the arrays that you're working with, and so on and so forth. You can provide the signature of the arguments that go into a function, for example, but you don't have to. So again, so number tries to be clever by the default, but you can specify further information if you want to. Yeah. So number also tries to, so it tries to create, again by the default, it tries to generate high-performing code. If it doesn't manage, so there are some cases where it's not possible, then it just falls back to a standard Python version. If you want to enforce that that number uses the Cython, the C versions, then you can pass in this flag, no Python equals true. And then if it fails to generate high-performance code, then it will crash. Right? So that's, if you don't have that, then it will, and it's not possible, then it will just run the Python code. If you have that flag, then you will get an error instead. So here are some of the questions that were asked. So you can, by default, you don't have to do much, but you can, for example, provide function signatures explicitly. You can even generate GPU code, CUDA code, and even CPU parallel code. I think both of these are somewhat experimental, but it might be fun to try these out. It is possible to call out to external C functions. You can compile things in advance. So this was the question regarding if you don't want to time out, if you want to avoid timing the compilation process, you can compile in advance, but you can also cache the compiled code. There's also vectorization of functions, so this is important when you work as NumPy arrays. So there's a similar vectorized decorator that you can use in number. And so there's a lot of documentation, and I think it's actually fairly well written. So I recommend you to just go to the documentation page. So, okay, number pros and cons. So it's a just-in-time compilation that is extremely simple to use, and it's highly automated. So there's almost nothing you need to do, but also nothing you can do in a way. Well, maybe it's minor disadvantage. It's external dependencies and quite a complex one. So you need kind of LLVM and yeah. So in Conda it's easy, but if you don't have Anaconda, then it might be a bit more difficult to install. I've also seen that if you're really good at Cython, then you might actually get better performance with Cython. But I'm not 100% certain about that. So it'll be interesting to see actually which one of them are more performant for your assignment. Yeah.
About that it needs to be installed as an external dependency. Will it run on the Linux computers?
So you asked. Okay, so you're asking if Numba is available on the EFI computers. Yeah. So if you have Anaconda, if you install the Anaconda distribution, then you should be fine. I'm pretty certain, so you still need the LLVM. No, but I think Conda even installs LLVM for you. So I think as long as you use the Anaconda distribution, which you can install locally for your user, then you'll be fine.
Okay, but I'm more wondering, since because of the requirement of all handles that you need to be able to run on the EP computers just in general. So that's a requirement for most tasks, I think.
Sorry, come again?
I think it's a requirement if we're going to deliver tasks,
Yeah.
then it's required that they're able to run on the EP Linux computers.
Yeah.
So unless that's the default by the EP Linux computer, I don't think the assignment will be accepted if it doesn't run automatically.
So are you asking? So
Okay, I can take it.
yeah, let's take it afterwards. But in general, so for these kind of things, if you have troubles, I really recommend you to just install the standard Anaconda distribution, both on EFI, but also on your local computer. It'll make your life easier. Okay. Any questions? No? Okay, let's stop. See you in probably 4 weeks or so. Bye.